So the next mathematical statement states, prove the following assertions by using mathematical induction that the left is the same as the right for all n, which is an element of positive integers. So I'm going to start off by saying let Pn be the statement and this is the statement. Now we're going to prove true when n equal 1. So we're going to prove when n equal 1. Now, when n equal 1 on the left-hand side, it's already worked out. This part is when n equal 1. But you could have done it where you substitute 1 here, but it's already here. So for the left-hand side, we already have 1.2, which is 1 times 2 to give me 2. For the right-hand side, we have to substitute. So replace here to be 1, right here to be 1, and right here to be 1. So you have 1, open bracket, 1 plus 1, 1 plus 2 over 3. So 1 plus 2, that's 3. 1 plus 1, that's 2. So 2 times 3 is 6. Times 1 is 6, divided by 3. So I get my 2. So we have proven that the left is the same as the right. Now the next step is to assume true. So assume true when n is equal to k. So when n equal k, where I have n here, I'm going to replace it to be k. So I have 1.2 plus 2.3 plus 3.4, and it continues, plus k, open bracket, k plus 1, equal, numerator I'll have k into k plus 1. So the numerator I have k into k plus 1 times k plus 2 all over 3. So that's my assumption. So now I am going to prove true when n equal k plus 1. So prove true or n equal k plus 1. Now we have to show that the left is the same as the right. So let me adjust my screen. So for the left hand side, I'm going to replace k plus 1. So I have 1.2 plus 2.3 plus, I'm going to leave this off for the sake of space, plus, instead of n, I'm going to have k plus 1. Remember, I replace k plus 1 for n. So by right, this is being replaced with k plus 1. So just remember, I have n times n plus 1. So because I replace here to be k plus 1, and inside the next bracket, I will have k plus 1 for n, and then an additional plus 1. So this 1 plus 1 will become 2. So right here, I will have k plus 1 times k plus 2. So that represents the left-hand side. For the right-hand side, I'm going to do the same thing, where I see n, I am going to replace it with k plus 1. So I'll have k plus 1 here. So what I did was replace this kn with k plus 1, and this n plus 1, it becomes k plus 1 plus another 1, because we replace this n with k plus 1. The n plus 2 now, I will have k plus 1 plus 2. All over 3. So what's happening here, I replace this n with k plus 1, this n with k plus 1, and then the additional 1, and then this n with k plus 1, then I have plus 2. So that means on this side, simplifying, I would have k plus 1. I will have here k plus 2. And then the final one will be k plus 3. And it will be all over 3. So that's what I'm trying to get on the left-hand side. Now, on the left-hand side, with a series, let me just go ahead and erase the top. So with a series, if we talk about it going from 1 to k plus 1, what happened with a series? You have, say for example, you have 1 plus 2 plus 3 plus 4 plus 5. If I want to split this, I can say the summation from n equal 1 to, this is the 4 terms, so say n equal 4, and whatever is the formula I use to get this trend. So from here to here would represent this series, and then I never include the 5th term, so I'd have plus 5. So what happened is that we can break this to become the series plus the term. Now the series plus a term means the series from 1 to k plus my k term. So I can break this down to become the series 1 times 2 plus 2 times 3 plus 3 times 4 dot plus k into k plus 1. So this portion that I have here represents a series from 1 to k. But because this represents the series from 1 to k plus 1, so that this represents the same, I'd add the k plus 1 term, which would be just this little portion here, which is k plus 1 times k plus 2. So this portion that I have here, it's the same thing as the assumption, where the left is the same as the right, so I can replace right here with k times k plus 1, k plus 2 over 3. So that's coming from the assumption. Plus, I have my k plus 1 times my k plus 2. Now we can now factor out what's common. If you look, k plus 1 and k plus 2 is common. So I can factor out k plus 1, and I can factor out k plus 2. When I factor it out, on this side, I'll be just left with k over 3. And over this side, because I took out both brackets, it would be just plus 1. So simplifying this, put this as 1 over 1. So the LCM is 3. So 3 into itself goes 1 time. So 1 times k is k. Plus 1 into 3 goes 3 times. So 3 times 1 is 3. And then we have the k plus 1 and the k plus 2. So if you look at this is my left-hand side. And for my final result, I have the left-hand side. This is the same as the portion I have here, which is the right-hand side. So because they're the same, we have proven it. So what is this saying? We will have our final statement to say, since true when n equal 1 and assumption true when n equal k, and it is proven true that it is true for n equal k plus 1, we can conclude that it is true for all positive integers. And that's how we prove it. And don't forget your statements. Thanks for watching. Don't forget to like and subscribe to my channel.